Hi, everyone. In this video, I will be giving a demonstration of Poisson and negative binomial regression using SPSS. So whether we're using Poisson regression or whether we're using negative binomial regression, we're going to be using the same data set with the same basic example. Now, before we get started, I do want to mention that underneath the video description, you'll find a link to the SPSS data file that I'll be working from in this video presentation, so you can download a copy to follow along. You'll also find a link to a PowerPoint that I put together that really is designed to provide a much deeper dive with respect to interpretation of the results and so forth. So as I go through this presentation, I'm going to be talking some about how to interpret and so forth, but I'm going to be focusing a lot more on the procedural aspects of running the analysis. So I do encourage you to download a copy of the PowerPoint for a deeper dive. So in terms of our example, we're pivoting off of one from Long and Free's example from 2014. This was actually associated with their book, Regression Models for Categorical Dependent Variables Using Stata. And the example and the data also appear to be based off of an earlier study by Long from 1990 on the origins of sex differences in science, which was published in Social Forces. So for our general example, we're basically studying predictors of graduate student productivity, which is indicated by the number or count of predoctoral publications. So the dependent variable in our analyses is going to be this ART variable that you see in your data set. That is referring to the articles or number of articles. And we're essentially looking at number of publications during the last 3 years of graduate school. So the predictors in our model are going to include gender identification, which is the variable female in the data set, which is coded 0 for male, 1 for female. Marital status at the time of PhD completion, which basically is coded 0 for else or not married and 1 for married. The number of kids aged 6 or under at the time of PhD completion, that's the Kid 5 variable. The number of articles the student's mentor published in the last 3 years prior to PhD completion, that is associated with the mentor variable in the data file. And then we also have a variable reflecting the prestige of the PhD program the student had attended. So PhD is basically regarded as a continuous variable during our analysis. So you can see a subset of the data file that we're using that's displayed on your screen right here. So here we are in SPSS, and the variables that we are working with, like I said, we have the ART variable. That's the number of articles published in the last 3 years of the PhD program. We have female, married, Kid 5, PhD, and mentor. So all of these are our predictor variables. And so each row basically just represents a different person who was who had received their PhD. So we're going to start out with just running our analysis using Poisson regression. So to do that, we're going to go to Analyze. We'll go down to Generalized Linear Models and then click on Generalized Linear Models. So we'll click on that right there. And so in terms of our specification here, under type of model, we're going to click on Poisson log linear. So it may be a little tricky to see right here, but basically we've clicked right here under counts because our dependent variable in our model is a count outcome. So we're clicking on Poisson log linear right there. Next, we'll go under the response tab and we'll move the article variables over to the dependent variable box. So I have the little ruler next to articles, by the way, is just capturing the fact that this is essentially a discrete ratio variable, but it's but we use that little ruler indicator for either interval level or ratio level variable. So that's why we have that set in that fashion. Next, we click on predictors and we're going to select gender, married, number of kids, PhD prestige, and mentors number of articles. And I'm going to move all these over to the covariates box. Now, oftentimes I'm asked, why are we treating gender and married and like in this fashion right here? These are obviously binary categorical variables. Why are we not moving them to the factors box above? And we could do that, but it's perfectly permissible. If you have a binary predictor variable in your model, you can just treat it as a general covariate. Just kind of keep in mind that, if we moved those two variables up to the factors box, if we generate our output, the reference or baseline category actually would be the highest category for each of those variables. And my preference generally is to treat the category that's coded 0 on the original variables as my baseline or reference category. So that's why I'm doing it in this kind of way. But obviously, if we happen to have multi-categorical variables where we have more than just two levels, then we would generally want to utilize the factors option, or at least do whatever necessary recoding through dummy coding in order to include them in the model as covariates. So next we'll click on Model, the Model tab, and I'm going to highlight all of these our variables right here and move them over to the model box. If I don't do that and I try to run the analysis, what I'll end up doing is just generating results for an intercept only model, which is essentially a model with the intercept and no predictors in the model. So that will be relevant later on as we talk, but for right now, we want to actually include our predictors. So I'm going to move these over. And then under the estimation tab, we're going to leave pretty much everything as is. We'll go under statistics, and then we'll click on include exponential parameter estimates down at the bottom. So the thing is that when we run our analysis, if we don't click on this, we're going to get the regression coefficients and tests. However, the regression coefficients sometimes are a little trickier to make sense out of in the context of Poisson or negative binomial regression. They're essentially the predicted change in the log count on the dependent variable per unit increase on a predictor variable. And sometimes that throws people off, or maybe it's just not as an intuitive way of talking about the relationships between the predictor variables and the outcome variables. So if we click on include exponential parameter estimates, we generate an index that's called the incidence rate ratio, which basically refers to the multiplicative change in the incidence rate or count on the dependent variable per unit increase on a given predictor. And this is, again, holding all of the other predictors constant. So at any rate, what we'll do now is we'll click on OK to generate our output. So we'll scroll down here, and you'll just kind of notice, first off, let me actually scroll up, just the model information above. It says dependent variable, it's got the name, probability distribution is Poisson, and we have the log link function. We have some continuous variable information, basically just some information about the mean standard deviations for our variables. Then we have this box called goodness of fit. And so these are basically indices of the fit of the model, and they're not terribly helpful when it comes to evaluating the fit because the numbers themselves oftentimes are just they're kind of decontextualized. They're really, oftentimes they're more beneficial in the context of making comparisons between models. But one index that I do want to draw your attention to is this Pearson chi-square to degrees of freedom ratio. So this value right here. So one of the assumptions of Poisson regression is that of equidispersion. And what that basically means is that the conditional variance and the conditional means for our dependent variable, those are equal. Okay, so if you happen to have a situation where the conditional variances are exceeding the conditional means, that is referred to as overdispersion, and that can translate in terms of interpreting our regression model, that can translate into decreased standard errors or downwardly biased standard errors and inflated test statistics and confidence intervals that are too narrow. So that can result in an increased type 1 error rate when you are judging the significance of your regression parameters. So this index right here If the value is 1, that or close to 1, that would be signifying a case where you have more evidence of equidispersion, which is a good thing in the context of Poisson regression. But if the value is greater than 1, and perhaps more substantially greater than 1, like you might see right here, then that would be evidence suggesting that we have an over-dispersed model. And so then that draws into question about, how much can we trust some of our decisions when we are interpreting those regression parameters. So the negative binomial regression, by the way, the idea behind that is to deal with that particular problem. It helps essentially with negative binomial regression. The idea is to adjust for over dispersion so that we can have more trustworthy interpretations of our regression results. So we're sticking with Poisson right here just to kind of introduce you to a lot of these different concepts. Later on, we'll run the negative binomial regression, but I do want to draw this to your attention. If you happen to decide that you're going to run a Poisson regression and you find a situation suggesting over dispersion, then that does kind of call into question some of the decisions that you might be making with respect to the regression parameters in terms of statistical significance. So we'll go ahead and scroll down a little bit further, and you'll notice that we have this little test down here. This is a likelihood ratio chi-square test. And basically, this is a test of the overall fit of the model to the data. The idea is that we're testing our model containing all of our predictors. Basically, it's a full model relative to a null model or an intercept-only model. So basically, that's just a model with no predictors. And this test is essentially allowing us to test whether our model that contains the full set of predictors represents a statistically significant improvement in fit relative to a null model. And you can see that likelihood ratio chi-square test value right here is 183.034. We have the number of predictors in our model, which is 5, and you can see we have statistical significance. So that's basically indicating that our model does represent a significant improvement in fit relative to a null model. Now, one of the kind of frustrating things sometimes might be in the context of using SPSS is that you're kind of stuck with this particular test if you want to make an assessment of the fit of the model. In other programs like Stata, you can actually generate another index, which is referred to as McFadden's pseudo R-square. And McFadden's basically provides kind of a more descriptive approach to judging the fit of a model. It basically represents the proportionate improvement in fit of our model containing our predictors relative to a null or intercept-only model. And unfortunately, you can't generate that directly in SPSS, but what you have to do is you can actually calculate it. So I go into those details in our PowerPoint, and I will kind of show you this well, actually, I'll just go ahead and show this to you now. Why not? So what we need in order to compute McFadden's are basically two values or two measures. We need the log likelihood that you see right here from our current analysis, and then we need the log likelihood from associated with an intercept-only model. So what we'll do is just really quickly, we've got one value already. Now we need to generate the value for our intercept-only model. So to do that, we'll go back and go under, let me see if I can highlight this, generalized linear models. Under predictors, we'll leave that alone, but we'll move under the model tab all of these out. So we'll highlight them, click on the arrow key right there, and click on OK. And you'll see a little box that says no effects have been specified. Therefore, an intercept-only model will be fit. Do you want to fit it? Yes. So now when we scroll down, you'll notice that only the intercept appears in the parameter estimates table. So this is our intercept-only model. And you'll notice, too, that we've got the log likelihood right here associated with that particular test. So as I said before, in the PowerPoint that I put together, I kind of go through the computations, but I've also developed an Excel file that will quickly calculate our McFadden pseudo R-square for us. So this is it right here. If you download it, all you need to do is to make substitutions of values in the yellow area only. So do not change anything else, because if you do, you end up changing the calculations, and that's not something we want to do. So for our intercept only model, the log likelihood was negative 1742.573. So that's it right there. Let me make sure I got that right. Yes. And then for our full model, we have negative 165.056 right there. And so we get that value. Okay. Excuse me. Actually, that's incorrect. I think I inadvertently missed a number in there. All right. Let me try that again. Never fails that you can end up making a little error somewhere in all of this. So it's actually negative 1651.056. So now when I substitute that in, you can see the McFadden pseudo R-square value is 0.0525. So, you know, in a nutshell, we might say then that our model that contains the full set of predictors represents approximately about a 5% improvement in fit relative to a null or intercept only model. So at any rate, so you can use that in addition to the likelihood ratio chi-square test in order to make a statement about the fit of your model. So at this point, let's go back to our output, and we don't want to be interpreting the intercept only model. We want to go back to our full model. And now we're going to look at the output containing our parameter estimates. So in the various columns, you'll notice that we've got over here, we've got the B's right here. These are the unstandardized regression coefficients. We have the standard errors. We also have a confidence interval that's formed around the regression coefficients. The hypothesis test is carried out using Wald chi-square right here, which is essentially the square of the ratio of the unstandardized regression coefficient to the standard error. So that basically provides the chi-square value, and each of these tests are single degree of freedom tests, and you'll notice that we've got our significance level over here. You'll also notice that we've got this EXPB column right there. These are referred to as the incidence rates ratio associated with each of the predictors. So I'll just denote this as IRR right there. You'll also notice that we have you know, a confidence interval that can be formed around the incident rate ratio as well. So just kind of going through very generally in terms of interpretation, we'll go ahead and just look at mainly the regression slopes associated and the IRRs associated with the individual predictors. So just kind of keep in mind too that the regression slopes for our predictor variables represent the predicted change in the log count on the dependent variable per unit increase on a predictor variable. So the term log count sometimes throws people, but essentially what we're doing is we're modeling a nonlinear relationship between each of our predictor variables, our independent variables, and our count variables. So basically when I refer to a log count, we're referring to a transformation of the count variable. But generally speaking, you can still interpret the positive and negative coefficients as reflecting, you know, positive or negative relationships with the count variable. But you can't use the actual numeric value to refer to the actual change in the count, but rather it's the change in log count. So as you can see right here, for our gender identification variable, the regression slope is negative 0.225, signaling a negative predictive relationship between gender identification and the number of articles that were published in the last 3 years of the PhD program. So because of the coding, you know, remember that those identified as male were coded 0, those identified female coded 1. So because that regression slope is negative, that's signaling that students who were female at the time of at the conclusion of their PhD program were predicted to publish fewer articles or have published fewer articles than males. And so in terms of the incidence rate ratio right here, you can see that basically you could think about it as the multiplicative change in the incidence rate or count per unit increase on a predictor variable. So basically females were predicted to publish about 0.8 times as many articles as those identified as male. Now, in terms of the statistical significance for our regression coefficient right here, we have our Wald chi-square test value right there. There's our degree of freedom that was referenced, and then the p-value right there. So you can see that gender identification was a negative and significant predictor in our model. And again, the indication is, based on our results right here, is that females published fewer articles than males, or at least they were predicted by the model to publish fewer articles than males. Next, we'll look at the married variable right here. So if you were married at the conclusion of your PhD program, is that predictive of the number of articles that were published? So you'll notice we have a positive coefficient right there, signaling a positive relationship between marital status. Basically, individuals who were married were predicted to publish more articles than those who were not married at the conclusion of their PhD program. You'll see with the Wald test results right there, you'll see that we have statistical significance. And so we have a positive and significant predictive relationship. The incidence rate ratio right there is 1.168. So basically, students who were married at the time of degree completion were predicted to publish about 1.17 times as many articles as those who were not married at PhD completion. Then we have the number of kids less than 5 at the time of PhD completion. The regression slope is negative 0.185, which would then suggest that having more kids under 6 at the time of completion would be associated with fewer publications. In terms of the significance test right here, you can see that we have statistical significance. And in terms of the incidence rate ratio, basically for every additional kid that you had under 6, the predicted count in terms of the number of articles published changed by a factor of 0.8. So in other words, that 0.8 is signifying a decrease in the number of articles published per additional child you had under age 6. Then you have this PhD prestige. The regression slope is 0.013, and you'll notice that this variable is not statistically significant. So I'm not going to go any further on that one right now. You'll see also with the mentor's number of articles, so is the regression slope is 0.026, and we have statistical significance. So in other words, basically, students who had mentors that had published more articles were predicted to have published more articles by the end of their PhD careers, or by the end of the 3-year period prior to completion of the PhD. So you'll also see the incidence rate ratio of 1.026. So again, that's just signifying that we have a positive relationship between the mentor's number of articles and the student's number of articles at the end of that PhD period. So that's basically our Poisson regression. The next thing that we're going to do is move on to computing the negative binomial regression. So to do that, we're going to go up to Analyze. We'll go to Generalized Linear Models. Again, click on that. And we're going to also move all of these variables back over to the Model tab. So we're going to leave everything as we had before. The only difference at this point is under Type of Model, we are going to select Custom. And where it says distribution, we will select negative binomial, and the link function, we will select log. Now, you'll notice that up here at the top, it says counts, and it says negative binomial with log link. And you could do that. The thing is that when you're carrying out the negative binomial regression, what occurs is the estimation of a dispersion parameter, which is designed to kind of capture or estimate the amount of over dispersion in your data. If you remember what I was saying before, over dispersion in the context of a Poisson regression can lead to downwardly biased standard errors and basically inflated type 1 error risk when you are interpreting your regression coefficients. So if you select this option in the counts, under counts, the dispersion parameter will be basically fixed to 1. So in the context of a Poisson regression, the dispersion parameter is essentially 0, meaning that there's no expectation of any over dispersion or anything of that nature. So if you select this under negative binomial with log link in the counts section, it's going to just kind of say, all right, we're going to assume over dispersion parameter of 1, and we'll estimate the model from that. But it could be that, you know, the level of over dispersion falls somewhere between that 0 and 1, or maybe is greater than, even possibly greater than 1, or whatever. So to get a little bit more precise estimate, my preference is to go down to custom, where it says distribution, select negative binomial, under link function, select log link. And then you'll notice that by default, you know, if you stick with this right here, where it says parameter specified value, which is set to 1, well, that would be equivalent to this setting up here. Essentially, the over dispersion parameter is fixed at 1. Well, that's not what I want to do. I actually want to estimate it. So I'm going to click on estimate value down here. So basically, we are just selecting this option right there. And that's literally all there is to this particular change. So now what we'll do is we'll click on OK to generate our output. So as you're looking at the output, the general interpretation approach that I was using with the Poisson regression is pretty much what we're doing in the context of negative binomial regression. You'll just notice up here at the top where it says model information, it says probability distribution is a negative binomial. When we scroll down, you'll see we have our goodness of fit table. And you'll notice too that the Pearson chi-square to degrees of freedom ratio is much closer to 1 than what we had previously. So basically, in this particular case, after we utilize the negative binomial approach, the issue of over dispersion really appears to be much less of an issue that we have to worry about. So another thing that I want to draw your attention to is, if you recall earlier, I was saying that you could use some of these goodness of fit indices to maybe make comparisons between models. One index of fit that you can utilize is the AIC. Another one might be the BIC. These are two fairly conventional indices. And basically, what you would do is you would compare the AIC or BIC of this model against a competing model. So our competing model, let's just say it is our Poisson regression model. So the preferred model out of the two would be the one that has the lower AIC and BIC values. Now, if you look at the AIC and BIC associated with our negative binomial regression, we have 3135.917 and 3169.649. If we go back up to our Poisson regression, you'll see up here, the AIC is 3314.113 and the BIC is 3343.026. So clearly there's an improvement in fit of our model by using the negative binomial model as opposed to the Poisson regression modeling strategy. So we'll scroll on down, we'll look at our omnibus test right here, and you can see that the likelihood ratio chi-square test is indicating statistical significance. So we have a significant improvement in fit of our model containing the full set of predictors relative to a null or intercept only model. Now, as I mentioned before, you can also compute McFadden's pseudo R-square very easily. If we just scroll up here and obtain our likelihood, log likelihood value from our goodness of fit table, which is this right here. And then we also obtain the log likelihood value from an intercept only model. So I've got this value right here as negative 1560.958. We'll quickly generate the log likelihood for an intercept only model. So we'll go down to generalized linear models again, and under the model tab, we'll select all these, we'll move them out, and we'll click on OK and generate and click on yes. And now for our intercept only model, the log likelihood is negative 1609.937. Okay, so basically all we need to do at this point is to basically plug these values into our calculator, or you can use the formula from that's described in Appendix B of the PowerPoint. So let's go ahead and go back into our Excel spreadsheet right here for the intercept only model. The log likelihood was negative 1609.937. And for our full model that contains the full set of predictors, it's negative 1560.958. Okay, so now you can see McFadden's pseudo R-square value is 0.03, meaning that our model containing the full set of predictors represents about a 3% improvement in fit relative to an intercept-only model. And keep in mind, too, that the pseudo R-square is not to be interpreted in the same way that you interpret R-square in the context of least squares regression. In the context of least squares regression, the R-square value represents the proportion of variation in the dependent or criterion variable accounted for by the predictors. We're using the pseudo R-square to reflect the proportionate improvement in fit of a model relative to a null model. And so that's kind of a different, it's computed differently in the context of negative binomial and Poisson regression. Okay, so now we'll go back up to our previous results for our full model. And if we look at the parameter estimates table, you'll notice that it looks very similar, except that, you know, some of the values are changed, obviously, because we're using a different model. You'll notice that down here, this is the dispersion parameter. So it's basically an attempt to estimate the amount of over dispersion. So basically, with that estimate, then we have corrections that are made in the other parts of the table. So without going too far into everything, we'll just kind of go back and just take a quick look at gender identification. That was a negative, and a significant predictor of the log count of the number of articles, or if you want to just think more generally of the count of articles. You can also see the incidence rate ratio right there is 0.8. If we look at the married variable right there, you can see it's a positive, and it's a positive predictor in the model, but it's not a statistically significant one. You'll see the significance level right here is 0.067, so it would not be significant at the conventional 0.05 level. There's our incidence rate ratio right there. If we look at the number of kids, we have a negative predictive relationship between the number of kids and the number of articles published. You can see that that is statistically significant. And with PhD prestige, you can see, you know, it's there. We have a positive regression slope, but obviously it is not statistically significant. And then when we look at the mentor's number of articles, we have a positive coefficient right there, indicating a positive relationship between the number of articles published by a mentor and the number of articles published by a student by the end of their graduate career, or at least by the end of the 3-year period of their graduate career. So you can see that we have our statistical significance right there. Once again, these are the incidence rate ratios, and I'll leave those to you to interpret in the context of the video, but I do go into those more in depth in the PowerPoint. Okay, so at this point, one question we might have is whether our model, our negative binomial model, fits significantly better than a Poisson model. Okay, so that might be a reasonable question. If you so one thing that we can do is we can test the dispersion parameter that's estimated right here to determine if, you know, really does it make sense to go with a negative binomial model. So keep in mind that the dispersion parameter right here that we have, which is 0.442, that's being estimated within the context of our program. As I mentioned before, though, a dispersion parameter value of 0 is consistent with a Poisson regression model. So one thing that we can do is we can perform a likelihood ratio test where we compare a negative binomial model where we have our estimate right here against a negative binomial model where we have fixed the dispersion parameter to 0. So in other words, what we can do is we can use the log likelihood from those two models and perform a likelihood ratio chi-square test. And so I go into that discussion in the appendices of the PowerPoint, but I also have it set up to where I can do that using the Excel file. So I'll just go ahead and just briefly demonstrate that process. So right now we do have the likelihood or the log likelihood for our current model where we have estimated the dispersion parameter. So our log likelihood for this model is the negative 1560.958. So now what we need to do is to generate the log likelihood for a model where the dispersion parameter is fixed to 0. So to do that, we can go to Analyze, Generalized Linear Models again. Under okay, so this is from the intercept only model. I need to move all these back in. And so basically going back to our negative binomial model, our full model, but under type of model, we need to go down to where it says custom and then down to parameter down here. And where it says specify value, we're going to remove the 1 and we're going to put a 0. So when we click on OK right now, then when we scroll down, you'll see that the dispersion parameter is fixed to 0. So now we have a model where the dispersion parameter has been estimated, and we have a model where the dispersion parameter is fixed to 0, which is consistent with a Poisson model. So now all we need to do is to obtain the log likelihood from this. So that is the negative 1651.056. So what we'll do now is we'll go back into our Excel spreadsheet right here and go down to the next set of yellow lines right here. And so for the first one, it says basically I have two models, a reduced and a full model. The reduced model is the one where basically we are fixing that dispersion parameter to 0. So the in terms of the this particular model, the log likelihood was negative 1651.056. Okay, then for the full model, the log likelihood is negative 1560.958. All right, so we do that, and so you'll see that we get, I've set it up to we've computed the likelihood ratio chi-square value. There's our degrees of freedom. It's going to always be a 1, so that's just set by default. And then the p-value right here is the computed p-value. I just have it set up so you can report this as, we have a statistically significant difference in the fit of the models. Basically, it's favoring the negative binomial model where we have estimated the dispersion parameter, and so you can report that with a chi-square of 180.196, degrees of freedom of 1, and p less than 0.00001. So there you go. And really quickly, by the way, I do want to mention too that as we're carrying out this test right here, if you want to talk about the fit of one model relative to the other, if you're using the log likelihood over here, basically the log likelihood that is for the model that is further away from 0, that is the worst fitting model. So the log likelihood you'll see of the reduced model where we're estimating the where we're fixing the dispersion parameter to 0, you'll see it's negative 1651. That distance from 0 is greater than the distance for the full model where we are estimating the dispersion parameter. The distance from 0 here is 1560. So you can see that if you just take the absolute values right there, this distance from 0 is smaller than this distance right here. So that's how I arrived at that statement about our full model representing a better fit relative to the reduced model. All right, so that's going to pretty much wrap up this video presentation. I hope that you got something out of it. And once again, if you check underneath the video description, you'll find a link to the SPSS data file, the PowerPoint I referred to, and then also to this Excel file. So thank you all for watching, and you guys have a great day.